everyone, welcome back. In this particular video, we will be discussing the problem. Find first missing positive number in an array. We are given an unsorted array of integers. What we need to do is, we need to find the smallest missing positive integer. That is among the unsorted array having different values. The smallest value which is missing, but which should be positive integer, that is greater than equal to 1, which is missing in the array. The space complexity need not be constant. It is given in the question itself. You can take extra space. It necessarily need not be constant, but you can also implement a linear space complexity solution also. That is, you can take extra space. If you want any other data structure or any other array, you can create it. The input format will be having two lines of input. First line will be containing the integer n, representing the number of elements in the array. Second line will contain n space separated integers. Let's say there are 4 values in the array, 3, 4, -1, and 2. So this is the unsorted array, as you can see, having values 3, 4, -1, and 1. What is the smallest missing positive integer? So in order to find the smallest missing positive integer, let's start from the smallest positive integer, that is 1. Is 1 present in the array? Yes, 1 is there. What about 2? Is a 2 present in the array? 2 is not present. So 2 is the answer. That is the smallest missing positive integer in this array is 2. So given any array, you have to find the smallest such number, and it will always exist. Like some number will not be there, obviously. So how we can do it in extra space if you want? First of all, if we are not taking any extra space, if we are just saying let's do it in place, what can be a brute force solution? Let's take a bigger array for that matter. So I am saying a array containing 5, 3, 1, 2, 7, -3, 0. Let's take 4. So this is the array, let's suppose. And what we are having is these values. How many values are there in this array? 0, 1, 2, 3, 4, 5, 6, 7. So n is equals to 8. Arrays of 8 size. What is the smallest missing positive integer? How we can figure out it in the brute force solution? Let's start from the smallest number and search for it. Is 1 present in the array? So I will run a loop to search for 1 in the array. Is it 1? Is it 1? Is it 1? 1 is found. So since 1 is found, 1 is not the answer. 1 is there. Let's now search for 2. Is a 2 present in the array? 2 is not there, 2 is not there, 2 is not there. Finally got 2. So 2 is also present. It is not missing. We have to find the smallest missing positive integer. So we are starting from the smallest positive integer and searching whether it is there or not via simple linear search. Again and again search for 1, 2, 3. Now search for 3. 3 is also present. Then we will search for 4. So 4 we can say 5 is there, 3 is there, 1, 2, 7, -3, 0. 4 is also there. What about the next value, which is 5? As you can see, 5 is just present at the 0th index itself. Then next value we can say will be 6. But as soon as we are searching for 6, 6 is not present in the entire array. Even if we run a loop entirely, 6 is not there. So 6 is actually the answer, the smallest missing positive integer. So what will be the time complexity in order to do this brute force? See, since we are running a loop for 1, then 2, then 3, then 4, then 5, then 6, how many times I have to run this loop? In worst case, we can say we have to run it for n times. Why? Let's suppose this value was not -3. Let's say this was 6. In this case, what will happen? If you will run the loop and let's say this is not 0, this is 8. You will first search for 1, present. Search for 2, present. Search for 3, present. 4 is present. 5 is present. 6 is present. 7 is present. 8 is present. And as soon as you say all the values from 1 to 8 are present with the array size 8, the answer will be 9. So in worst case, we have to search for 8 different values for array having 8 elements. Or if in general arrays having n elements, we have to search one by one for n different elements in worst case. And for searching each element, what is the time complexity? We can say linear, because it can go again for worst case all the values in the array. So overall time complexity will be linear plus linear plus linear plus linear. How many times? N times. So overall time complexity will be n into n, n square, quadratic time complexity. But what about the space complexity? In this solution, since we are not taking any extra data structure, we are not creating any extra space, we are not basically, we are actually just making a pointer running a loop on the input array. It is constant space, no extra space is there. But the point is, Can we do it better? Although not the most optimized manner, but can we do it slightly better? Answer is yes. Since in this given array, we are not ensured of a sorted nature. We are saying that the array is unsorted. How about sorting it? How about making it in increasing order? If I will make all the values in increasing order, it will become -3, then 0, then 1, 2, 3, 4, 5, and then 7 will be there after sorting the array. So what we can say, once the array is sorted, we for sure can say that all the values, whether negative, whether positive, will be in ascending order, in increasing order. And now searching is very simple. Now we can just search by running a simple loop. We have to ignore the negatives. We have to ignore 0, start from 1. So 1 is there. Okay. If it is there, good enough. If it is not there, it will be the answer. Why? Because we are sorted the array. We have already sorted it. We are having all the values in increasing order. Next value, if 2 is not there, 2 will be the answer. If 2 is there, search for next value. 3 is there, 3 is not the answer. 4 is there, 4 is not the answer. 5 is there, 5 is not the answer. 6 is not there, so 6 will be the answer. If let's suppose this value was 6 itself, so in that case, we can just return 7. That is the next possible value. So just sort the array. What will be the time complexity to sort the array? We can say in general, it will take n log n if we are sorting it using quick sort, merge sort, heap sort, better sorting algorithms. Or you can say in general, if we are using inbuilt sorting, it will take n log n time. Plus, searching for the missing element, smallest missing positive integer, will worst case take linear time. Just a single loop will be required. So n log n plus n, overall time complexity will be n log n in big O. That is worst case. What about the space? This was time. We can say, since we are not taking any extra space, we are just sorting the array, rearranging the elements. No extra space is there. That is constant space solution. But this is the second solution, a optimized solution. But is it the most optimized solution? The answer is no. There exists even a better solution. What is that? See, for sure, sorted nature will help us. But what if we are not sorting the elements? What if in the question itself it was said that we can take extra space? How about creating any data structure where we are visiting all the values whichever are present in the array? We have to just search whether element is present in the input array or not. And in order to search the value, we can just put it in a data structure which will help us to search from it. So what is the data structure which will get the element, whether it is there in that data structure in constant amount of time, or put any element in that data structure in constant amount of time? That data structure will be a hash set. That is, you can say, a hashing algorithm we can use. Why hash set? Set will only contain keys. That is, it will only have one type of value which we need to be stored, which we need to find whether it is present or not in the input array. So what we can do in the most optimized solution, let's just copy the array again. In the most optimized solution, we will maintain a hash set of integers. That is, we will apply hashing algorithm and just hash all the keys present in the array into the data structure. That is, we will store all of these values in the data structure. In how much time? Storing all the values will take linear time. Why? Because storing one value will take constant time in average case. Storing all the values will take linear time. So this is average case complexity. In hash map or hash set, we usually discuss average case analysis only. Then to search which value is the smallest positive integer, we can start searching from 1. Is 1 present in the data structure? Yes. We can get it in constant time whether it is there or not. Is 2 present in the data structure? Yes. Is 3 present? Yes. Is 4 present? Yes. Is 5 present? Yes. Is 6 present? No. So 6 is the answer. So searching will also take linear time. First, to put all the values, then to search one by one, linear plus linear, 2 times linear. But time complexity, as we can say, is even better than the previous one, because previous time complexity was n log n. Now it is n. On what cost? Obviously on the cost of space. That is, we are taking extra space of hash set. We are creating a data structure. So on the expense of extra space complexity, we are able to boil down the time complexity to linear. One follow-up problem which you can actually take up the same problem only is that, can you just do it without extra space? Can you do just take linear time in order to solve this problem with constant space in place solution? Hint will be, try to use the same input array. But for now, what we are going to do is we are going to stay with this particular solution with having extra space, and let's write the pseudo code. So in the first missing positive function, what we need to do? We need to create a hash set of integers. Let's say the visited integers. We will store all the visited elements in it to check whether it is there or not. So run a for each loop or a for loop. You can run any kind of loop. Run a for each loop over all values in nums array and just push them or insert them in the hash set. So insert value in the hash set, in the visited set. Once we are able to store all the values, now second loop will be to search starting from the smallest positive integer. So run a loop. Till then, we can say we are able to reach n. So run a loop from 1 to n. First search for 1, then search for 2, then search for 3, up till n. Because in worst case, if all values are there from 1 to n, answer will be n plus 1. If array was of 8 size, all values are from 1 to 8 in some order, answer will be 9. 9 is the smallest positive integer. So in the last, after the loop, we can return n plus 1, because if all values are there, obviously n plus 1 will be missing. If some value will be missing from 1 to n itself, so we will return within the loop only. So to check if the current value is present in the map or in the set or not. If it is present, what we need to do? We need to say just search for the next value. But if it is not present, if it is giving me false, then return the current value, return the value, because that is answer, because that is missing. So this is the instruction manual. We have already written the instruction manual. Now we will be writing the code in milestone number 4 in Java programming language. So we have to create a hash set of integers. So hash set angular bracket integer. Let's say the hash set is named as visited, because we need to visit all the values whichever there are present in the array. And this is the syntax to create an empty hash set. Once we have created it, we need to push all the values into it by running a for each loop over the array. So I will run a for each loop over the array, and I will just insert it by using the function add. Add is the function to add any value, to push any value, to insert any value into the hash set. And this add operation in average case in Java takes constant amount of time. So overall additions for all the values will take linear time, because constant plus constant plus constant n times will be order of n. Then we have to search which value is missing. So we can run a loop starting from value 1 going till value less than equal to n, and we will check if the current value is not present or not. So if the visited dot contains is the function to search whether a key is present or not, and we only need keys. That's why we are only making hash set. We don't need values. If we need key value pair, then we have to make a hash map. But for now, only keys is suffice. So visited dot contain the value. If it is false, if it is not there, then we have to say this is the answer, because it is missing. Because if it is not there in the hash set, it is not there in the array. And if it is not there, then it is missing, obviously. But if all values from 1 to n are missing, then for sure the answer is n plus 1. This is also a very good tricky case. N is nothing but nums.length. So we can just return nums.length plus 1. So if I will run this code for the normal test case, this is actually a corner case. For normal test cases, let's say the sample input output should be 2. Let's see what is the test case which they are giving us when we run the code. So there is some problem in the code itself also. So we are returning value, but variable name is val, not value. Let's run it again and see if it is now working or not. There will be some other error also. N is not declared, so we have to take it to nums.length, or we can actually also create n variable if you want. If I will run it again, hopefully this time it should work for sample test case. It is giving me 2. Let's do it for corner case, where all the values are present from 1 to 5. Array size is 5, and all values, if they are present, output should be 6, n plus 1. Let's see if it is giving me n plus 1 or not. It is taking some time to run, and it is giving me 6. So if I will submit it, hopefully it should work for all the test cases. Let's see. It is taking some time to run, but once it is run, we can ensure the time and space complexity taken by this. So as you can see, all the 21 test cases are accepted. The time complexity, first loop linear, second loop also linear, and both the operations add as well as contains are constant. So overall time complexity will be n plus n, which is 2n, which is still linear. What about space? Since we are creating a hash set, extra data structure on our own, the auxiliary data structure, the space complexity will be order of n, that is linear. So time as well as space both are linear, but as discussed in the approach video, there is a follow-up which you can do in order to solve this is this in linear time but constant space, that is without extra space. But that will be a extra thing which you can do, not required at this moment. This you can assume is the best possible solution which you can give in an interview. Till then, we can make this video till this point only. Let's meet in a new video with a new problem. Bye bye, take care.